So the one thing in summary that I think is just stunning from what you guys are saying is that the experiment that tests whether quantum mechanics is wrong is occurring, basically speaking, at the same scale as the experiment that tells you something about dark energy.
Yes.
That's absolutely insane.
Space-time physics will be also reformulating how we think about it from the point of view of quantum gravity. So I call the quantum gravity sort of the heart of physics because, you see, it's at the beginning. When we discover new things, we always go back in time, earlier universe.
Tristan, Djordje, Samir, welcome to the show. Samir, welcome back. Of course, you've been on many times. For those listening, a couple disclaimers. This is a little bit of a different episode. Tristan and Djordje have some new, I'll say for lack of a better term, physics things that they're writing a new book on. I'm not that smart, and so I've had Samir come to help me co-host. If you are listening on an audio-only platform, I recommend you use YouTube because there will be some kind of visual, not necessarily aids, but gestures and other things to help people understand what is going on. With that said, I'll turn over to Tristan and Djordje for quick intros, who you are and what you do. Samir, of course, you can do one as well. But Tristan, let's start with you.
Hi. Well, thank you very much, first of all, for inviting us to this podcast. I'm a professor of physics, mathematical physics. I came to this country, to the United States, from the other side of the pond, from a country that no longer exists, from Yugoslavia. I came in 1984, which is embarrassingly long ago.
So did I.
So 42 years, isn't that the ultimate answer to everything?
It is indeed.
So there we are. So 42 years later, here I am, still teaching physics and mathematics occasionally. Mathematical physics is my specialty. And there we are.
Very nice. Djordje?
Hi, Djordje Minic. I'm a professor of physics at Virginia Tech. And I came to this country in '88, also from that non-existent country anymore called Yugoslavia. And Tristan was the first person I met in Austin, Texas, where I came for graduate studies in University of Texas, Austin. And Samir was my classmate. That's how we know each other from graduate school. Yeah, I came after graduating from Austin, went to various places, New York, Chicago, Los Angeles, Penn State, and then ended up here in 2001 and have been in Blacksburg, Virginia Tech for the last, whatever, almost, you say 25 years.
Very nice. Samir, you want to do a quick one?
Yep. So I'll do a very quick intro about myself. You guys have heard this before. That's my book up there called The Science of Free Will. I am a physicist by training. I then became a hedge fund manager because they canceled the superconducting super collider, which meant that there was no job for me to have. And then in the last few years, I have gone back to physics. And so I am here to help Eric pass through some of the very clever stuff that Tristan and Djordje are going to be proposing in their new book.
Very nice. Question from the last guest. Samir, I'll start with you because we did a whole podcast on this, but the question is, do you believe in free will?
Very good. So it depends on what you mean by free will, doesn't it?
Yeah, well, you can go ask B for what she means by that,
Yeah,
and you can go listen to that podcast as well.
Excellent. Yeah, so I'll paraphrase my own book, which I encourage you to read. It's right up there. Basically, physics is deterministic. All the equations of physics are deterministic. And because all the equations of physics are deterministic, it means that every particle in your body is effectively following a deterministic physical law. We can argue a tiny bit about the collapse of the wave function. I have two physicists here, doesn't matter. That doesn't help you solve the problem of free will. So from the point of view of physics, you don't have any free will. However, having said that, there are three independent reasons for why you can never actually predict what a particular human is going to do, despite the fact that they're following laws of physics. And it is that precise lack of predictability that is your free will. So do you have free will? You do in practice and not in theory.
Djordje,
Sorry?
what's your answer to the question?
Okay, so this is a part of the book that Tristan and I, well, it's going to come out in July on July 15th. It's called Weight of Quantum, and we will talk in this podcast about the main message of the book. But there's something in that book we also are talking about, which is called like a mock quantum theory. Anyway, it's something that has to do with complex system. My intuition about this is that for complex adaptive systems, we have emergent probabilistic laws, but these probabilities do not have to be classical casino, Las Vegas type of probabilities. We'll probably talk about it a little bit in this podcast. And therefore, I could envision, okay, based on that expectation, this is not what Samir is talking about, that's something that is already established. But based on that expectation, if it's correct, that something like understanding of free will, consciousness, and things like that might emerge. So I would say, depending on the on the validity of those expectations, yes, I would say that there will be a new understanding of free will in the future.
Very nice.
All right.
Tristan?
I'll add to that, not just because I co-authored this paper with George about this mock quantum theory, but also because of another rather fascinating picture that I'm sure people have heard about, the butterfly effect and the so-called Lorentz attractor, where even in systems that are completely deterministic, you get this behavior that can be just baffling, where a system seems to be stuck in one type of behavior and then it kind of jumps at a rather unpredictable time and fashion into another state. And what I mean by that is that willy or nilly, we're not that idealized person who can have the initial conditions mathematically precise. We always have small errors in our measurements. So when we say that we know where we are and where we aim to go, we know that data only within some precision. And so there is always room for error. And I think that that's where free will does somehow creep in. Now, admittedly, our three very different answers perhaps are opening a subject for a totally different podcast. So I'm sorry if I'm derailing that. But at the same time, I haven't read Samir's book, so I'm now very much...
Unbelievable, Tristan.
Mea culpa, mea maxima culpa. But I'm now very much interested in reading it and, well, perhaps having a nice discussion with Samir subsequently.
Yeah, let's do another follow-up podcast on that.
After our homeworks are done.
Okay, so last kind of, for those listening, last kind of untraditional thing. Samir's got a couple of things that he wants to say, define some terms, give some context into what's going on. For you guys listening at home, we'll try and keep things... we'll dive into some of the nitty gritty, get in the weeds and some stuff, but we'll always try and bring it back so people at home can follow along, because hopefully your host, me, is also not lost. So anyways, Samir, I'll turn it over to you and then we can get started.
Okay, so I want to do a short intro at a reasonably high level into what Tristan and George, I believe, are saying. They'll correct me if I'm wrong, so that people can follow along. I should say that George and Tristan are two of my very oldest friends. George helped me through graduate school. I wouldn't have made it without him, so I'm deeply grateful. And their point is that they have a new way of thinking about quantum mechanics. And so here's the point. Einstein started a revolution first with special relativity, and he showed that length and time are affected by velocity. Basically, how fast you're moving affects how you think about your about distances and about times. Okay, very good. But in that formulation, space-time still obeyed basically Euclidean laws. Two parallel lines remain parallel, they don't cross, etc. The shortest path between two lines is a straight, shortest distance between 2 points is a straight line, and so on. Great. Then we had the next revolution, also from Einstein. He said, if you take some mass and you stick it into space, that mass or energy equivalently is going to distort that space. The geometry of that space is going to change. It's no longer Euclidean. Parallel lines can now cross. The shortest distance between two lines is no longer in general a straight line, etc. That's the general theory of relativity. Okay, now keep that in mind because this is critical. Now, let's talk about quantum mechanics. In quantum mechanics, you have the notion of something called a state. And a state is simply the list of variables that is required to fully describe the system that you're talking about. Okay, so for example, for a spinning electron, you would say that there's spin up and spin down, and you'd write the state as having the variables having to do with spin. Okay, great. So now, physicists like to always do clever things, and one of the most clever things that they do, it's a trick, which is a thing, nice way of saying clever thing, is convert a set of variables into a space. It's called a state space. So you pretend that that set of variables is not in fact just a set of numbers, it's a set of vectors that are all pointing in different directions. That's your state space. What we have done in quantum mechanics from the beginning is we have assumed that that state space is also Euclidean. That is to say, its vectors, behave in that abstract space the same way. Parallels don't cross, there's no curvature, etc., etc. And what Tristan and Djordje are saying is, hang on a minute, that's not necessarily true. It's not even necessarily being tested particularly well. This is the famous rule called the Born rule, by the way, named after Max Born, who was the grandfather of Olivia Newton-John, who, by the way, was the star of Grease and Saturday Night Fever. But anyway, let's put that aside. What Djordje and Tristan are saying is this hasn't been ever really A, tested, or B, thought about. What if that state space is curved? And what they're saying further is, if you assume that that state space is curved, some of the most complicated puzzles in physics, some of the deepest puzzles in physics, including the problem that we've never been able to combine gravity with quantum mechanics, might be solvable. And the fact that they can do this, that they can put it together, that they can use this perhaps to make a solution, actually has practical implications, because a practical person could say, listen, this is abstract stuff, what do I care? Well, interestingly, let me tell you something interesting, and after this, I turn it back to Eric. The iPhone you have in your pocket runs on GPS. It needs GPS for its location. But if we did not have Einstein's theory of gravity, we would not know the corrections required to the GPS satellite, to their timings, and your position would be off by many, many miles. So to put it another way, the mathematics that governs cosmology, that governs the universe, that governs black holes, that governs all these weird things, is the mathematics that is required for the iPhone in your pocket to work. So this is the fundamental reason you need to do physics like the type that Tristan and Djordje are doing. This is why it needs to be funded. This is why it needs to be thought about, because you never know what it's going to produce and how it's going to improve your life at some point in the future. So back to Eric to start the proceeding.
So to summarize, I'll go to you, Djordje, first. If we're at a dinner party or at a bar, and you have hey, tell me what you're working on, how would you describe it?
Well, yeah, thanks, Samir, for summarizing. Thanks, Eric, for asking that question. There are two parts here. Quantum mechanics is really the theory that basically tells us how things are built, let's say, of atoms. Everyone heard that there are atoms, right? And basically these little small things build bigger things. Atoms might be built out of smaller things, et cetera, et cetera. And then on the other side, we have gravity, which, as Samir said, has something to do with geometry of space-time. So we're trying to put the thing together, and what usually people have done in the past, they would take the rules of gravity, let's say, and then apply quantum mechanics. Or maybe they don't start with gravity, but something that maybe has a limit, Einstein's theory of gravity, and then apply the rules of quantum mechanics. What we are basically saying is that the first thing that you should find in trying to combine very, very small and very, very large is that the rules for probability, how probability is computed in quantum mechanics, okay, those rules actually become kind of what happens to the space-time geometry. They become dynamical, they depend on the context, etc., etc. And that can be tested in experiment. Okay, that's essentially our proposal. And that's why it's different, I would say, from many, many things that people are doing in trying to put quantum and gravity together.
Yeah.
I hope that was clear.
Yeah. So one thing that really caught my attention, you said this at some point in your work. You said the empirical knowledge of the quantum in quantum gravity is zero, period. That, I think, is a big deal. I think you should unpack that. Go for it.
Okay, so the interesting thing, like this problem, right, existed, and some people always even say that was Einstein's legacy, right, because he felt uncomfortable about quantum mechanics. We might touch about that, the nature, probabilities, etc. But obviously, he was the creator of general theory of relativity, and he wanted to put the two together. And he always wanted to start from start of general relativity and somehow change quantum mechanics to fit general relativity. I think he was not correct about that. But there, and people, of course, have proposed many theories. But the most interesting, and very ingenious ones, but the most interesting fact, as you say, Samir, is that if you look at the empirical knowledge about what is known about the quantum in gravity, let's say quantum for massive objects, okay, nothing is known. And one of the reasons is because technology hasn't been, it's not that people didn't ask the questions, people have asked maybe in the late 50s, 60s, but technology hasn't been around. And because of this, the use of quantum theory in technology that we're going through sort of rapid development now, people are only now asking very basic questions. Okay, so what are the quantum phenomena that happen with massive things? So the statement really is, as of this moment, our knowledge of quantum and quantum gravity really is zero. And we have to test some very, very basic things in quantum theory for massive objects for which gravity is important. And that's a thing maybe that sometimes people do not realize, but it is true.
So what's the pitch then? So supposing I'm a non-physicist, right? So what's the pitch? How does it relate to what Einstein did? What are you doing that's new, but at the same time related to what Einstein said or didn't say, as it were?
So as you mentioned in your introduction, in quantum theory is intrinsically probabilistic. What does that mean? Maybe I could do this illustration, the difference between quantum and the classical, and explain and also do the visual presentation. So let's say, for example, I crumple this napkin, okay? And I throw it. And what I'm doing is I'm throwing this napkin, and people who are following the video, they can see that there is a little trajectory of this napkin, okay? And every given point in time, as I throw the napkin, as you would throw the napkin, and every point in time, if you had a strobe, you would find napkin somewhere, exactly like you see the moon, moving, going around the earth or something. At any given point in time, you would find it somewhere. Now, the interesting thing about quantum mechanics is that if you were to apply this, let's say if this napkin were an electron, okay, you go down actually for the atoms, okay, the atoms are made of electrons and nuclei, etc. Okay, and if you were to try to throw an electron, you see, to go from a point, initial point, to the final point, electron doesn't follow one trajectory like your napkin does when you throw it. Okay, it basically takes any trajectory, okay, any path that would take you from the initial to the final, somehow sums it over it. Okay, that sum would compute something that when you square it in a particular way would give you probability for some events. What event would be that? Well, let's say, for example, you say like, what would be, if it goes any path, what would be the probability for the electron to go here? Well, I'm talking about probability because it can be here, it could be here, it could be over there, etc. Okay, so I have to basically sum all the possibilities. The probability is number between 0 and 1 that you sum to 1, also known as 100%. Okay, and the quantum mechanics computes that rule. And the rule is definite. It has to do with this flatness that you were talking about. It really is like Pythagoras' theorem, flat Euclidean geometry. Okay, but that rule, you see, forbids certain things that happen. And what we are saying is that rule, okay, will bend. It would curve. There would be a sort of if you want, Euclidean geometry, non-Euclidean rule, if you want, for the computation of these probabilities once you include gravity. Okay, and so that's the newest thing, and that has experimental implications that we can discuss later. I hope that was clear.
I think so. So Tristan, what actually bends these rules? In Einstein's theory, it's matter and energy that bend space, right? So what's happening here? What is bending state space?
It is the same thing that bends ordinary space. And I'll try to unpack that in just a second. But it is gravity itself. to a very good extent, we can think of this curvature, this nonlinearity that Djordje was trying to illustrate. We can think of that actually as the effects of gravity. So that's gravity by any other name, right? And we know that there is actually a very general, comprehensive, cohesive, and coherent theoretical framework in which both gravity and quantum mechanics do exist. We just haven't figured out many of the details, but we know that they do exist consistently together. It is called string theory. And in that string theory, the position in space, where exactly that napkin flies as Djordje is throwing it from one hand into the other, or if you're watching a ping pong game and you're watching the ping pong ball going from one racket hitting the table, getting to the other player, you can at every point specify exactly where that ping pong ball is. For elementary particles, somehow that gets fuzzed out, that gets very fuzzy, that gets somehow smeared out to the point where we are describing it as a wave sort of phenomenon. And so that's where that rule comes in for probabilities. Now, both of those spaces, the literal space through which we move and space-time in which we move and in which that napkin moved, in which that ping pong ball moves, and the electron, and also the matter itself, are in string theory described in a completely same footing. So we were talking about this earlier, and my personal epiphany on this is that how could possibly the space through which we move and the space of these material objects be subject to different laws? If Einstein has taught us that the space-time through which we move is bent, why shouldn't then the space of these matter degrees of freedom also not be bent? Agreeably, this is not a proof why it has to be like that, but it definitely could be, should be in all reasoning. So that means that that same thing that we call gravity should be bending all kinds of measurements of distance, because the probability, in a sense, is also a distance. If I tell you that, or George just told you he tossed the napkin from his left hand to his right hand, well, the initial position was in his left hand, the final position was in his right hand. There is a trajectory through which it went. And he was asking, well, what's the probability that this is exactly the path that he goes? It's sort of like a distance measurement. And if distances in space-time are bent, why shouldn't gravity also bend those other kinds of distances from one event to the observation of another event, which we in quantum mechanics call the probability of a certain outcome, given a certain initial assumption, an initial setup. Every experiment always starts with setting up the experiment, then letting it go. Something unfolds in that experiment, and then you measure the final outcome. And the probabilities are, in a sense, the distance between the initial and that final outcome that you observe.
So
go ahead.
In my head, when I listen to you talk about distances and space-time being bent, the pop physics in me goes to like the UFO videos and like the anti-gravity, that sort of thing. Like how, I mean, from your guys' perspective, like are any of these things possible? Like the things that are being thrown out there about whether it's like inter galaxies travel, or even like the way that the UFOs seem to move in some of the videos. Or like there's a TikTok, like a video from like 2004 where it like seems to be there and then all of a sudden it's over there, and it's basically just doing what you have described, but like obviously it's not a particle, it's a thing. Well, not obviously, nobody knows what it is, maybe.
Right.
Anyways, but like from your guys' perspective, like what, like how do you view those sorts of things when they come out? Especially recently, it's been all over the news, so that's where my head went.
For my own part, I'm a rather devout skeptic about news like that. I would, if there is definitely a photograph, a video, preferably with all kinds of measurements, that would be much preferable to witnesses saying that they have seen one thing or another. And of course, I understand that in many circumstances, there just aren't possibly any photographs or good videos or so. But let me answer the technical side of this question. So teleportation is definitely something that has been a buzz in recent news. I think the record is something like 1,200 kilometers distance. The Chinese have apparently managed to do entangling, and so what is referred to as quantum teleportation, but of a single elementary particle. I believe that particular experiment had to do with a photon. Now, you can perform tabletop experiments where that sort of thing happens, where a particle that you observe vanishes from here and it materializes over there without traversing the space from one location to the other. That's what you're referring to. So we know how to do that for elementary particles. You and I, my friend, are made up of what are referred to as Avogadro's numbers. So this is 10 to the 23, 24, 25 particles. What does that mean? That's sort of science gobbledygook at this point, perhaps for some in the audience. But that would mean 1 followed by 23, 24, 25 zeros. So we're made of that many particles. To make that many particles coherently vanish from here and rematerialize over there, I'm afraid you need something that in Star Trek they call a Heisenberg compensator, which is science fiction, or maybe some other gadget that is also known from science fiction. My favorite is Douglas Adams's improbability drive. So, in other words, we do not have by far the engineering of how to do that. The basic principle at the level where Djordje and I, fundamental physicists, the way we think about this, the basic idea of teleportation of single quanta is not really that surprising, and it can even be done in some laboratory experiments. But how to scale that up to something like, never mind you and I, but just a penny or something like that, that is very much in the realm of science fiction.
But is that an engineering problem or is that a physics problem at this point?
I believe it is. There is a very interesting science fiction book by Robert Forward, where he tries to classify different kinds of science fiction that science fiction authors use. And the lowest rung on science fiction is where the science fiction being described in the book is not against any known scientific principle. But not that anybody has even any idea, any model how to actually do that scientifically. Never mind the engineering difficulties, you start seeing how that hierarchy goes. And then finally, never mind the funding issues. For example, some of your audience may have read somewhere in Scientific American or so about something called the Alcubierre drive, which is very close to what Star Trek uses for warp drive. But in order to actually make that happen, you would need to have energies that are nowhere near available to the humankind. Even if we were able to pull together all our banks, all our bitcoins, and whatever else, and even if we were able to get all our political powers that be to work together, which of course is a huge if. So we're nowhere near that, but it's not exactly forbidden by any known science.
There you go, UFO people. Maybe somebody in a different planet did it. So he's saying there's a chance. Anyways, Samir, did you want to keep going on the train that you were at now before I needed to go get my UFO fix for the day?
No. So I guess the next question that we would ask is, why does anyone care, right? Quantum mechanics works, the iPhone works, the GPS works. What's breaking? Why do we need to put quantum mechanics and gravity together? What's the big deal?
Should I go, Tristan, or should you?
Well, my answer was going to be rather short in this respect. This is a little bit like that oft quoted, but maybe apocryphal story about Faraday, where he was asked at some point, what are these electromagnetic fields worth, or what are they good for? Supposedly asked by the prime minister in Britain at the time. And his response, again apocryphal, is that I don't know what it's good for, but I know you will find a way to tax it.
Which turned out to be true. We tax electricity.
Absolutely, absolutely. And of course, after Faraday, there are all kinds of other things, all kinds of other stories about Edison, Tesla, and Westinghouse, and lots of other folks who have worked on electrifying, if that's a good word to use, an entire continent and make it a household appliance. So I have no idea. I cannot answer how this quantum gravity that we are discussing, that we are trying to understand, how useful that will be in a future, but I'm sure that it will be useful. Besides your mentioning of GPS, I also wanted to point out that before the Apollo missions, computers were these humongous machines that were heating up entire rooms because they were made out of vacuum tubes, and they needed active cooling and all kinds of other, today, totally implausible scenarios. But in order to make those computing machines go up in a rocket, they had to be made small. And well, our friends experimentalists are ingenious enough. They figured out how to do it. So maybe passing back to George, if he has another tack on this, I will say, I'll pass our ideas on to our ingenious experimentalist colleagues.
Yeah, my feeling about this is that actually, in thinking of about this new sort of approach to quantum gravity, where we're basically saying that the rules of quantum theory should be made dynamical, the way you compute probability, and that will have experimental applications, that they will also shed light on quantum mechanics itself. And we are sort of going through a new phase in the development of quantum theory and its applications, sort of quantum technology, if you want, quantum engineering, quantum computation. And I think if we have a new way of seeing quantum theory, sort of from this quantum space-time point of view, this might be useful for folks like that. So it's not just some futuristic technology. It could be also just what we are people doing right now, but sort of understanding it from a deeper point of view, and then sort of shedding light on things that are maybe not understood as well. What Tristan mentioned is development of semiconductors, which replaced transistors, chips, right? Everyone knows about those, that replaced vacuum tube technology. I mean, that was really based on quantum theory. I mean, so people who work at Bell Labs on the first transistor, definitely they understood they had to use sort of rules of quantum theory as opposed to solid state physics, and that's how they made those devices. Something of that nature might happen, and something of that nature might require deeper understanding of quantum theory that this approach that we call gravitized quantum theory might offer. So there's something futuristic. I love these stories of Faraday and others, made up stories, but there's maybe something that is maybe closer to sort of the technology that people are trying to develop right now. We don't know. Okay, so I can maybe comment on something else that comes out from this experiment that we are proposing later on, that has to do with how we detect things. Like another thing that came out from quantum theory are microscopy. Like you use electron microscope to see, let's say, inside the cell. So this is a totally different field, right? It's a field of biology. It goes into medicine. Remarkably important, right? Seeing those little things in the cell, it's impossible to, unless you have an electron micro, unless you use this wave nature of the electron, the quantum nature of the electron, okay? Without it, it's impossible, okay? And I think something like that, this gravitized quantum theory, new ways of seeing things could be developed, and that's always useful, developing of technology like that, where that would be applied, who knows, but it's always useful. Anyway, maybe a long-winded answer.
So, George, let's talk about peas and potatoes.
Okay.
Because we have, that's the famous scene from the Hawking film, right? When Hawking's wife is trying to explain what it is that Hawking does, And she says, there are peas and there are potatoes, and he's trying to put the peas and the potatoes together. The peas are the little thing, the potatoes are the big thing, and he's trying to combine them. Okay, so we have a spectacular theory of the small, right? Quantum mechanics.
Yes.
We have never, ever found a single experiment that's ever contradicted it.
Absolutely
which
true.
Which is just insane.
Yes.
We also have a spectacular theory of the large, general relativity. And we have also, so far, with a couple of caveats, ever found an experiment that says, or an observation that
there's no experiments that contradict it. That's true.
Exactly. But we can't put them together, right? And so there are three reasons, right, that we want to put these together, at least three big reasons. So why don't you go into what those are?
Well, okay. So, one interesting thing is that, of course, general relativity has, in some sense, made cosmology, study of the whole universe, into a scientific field. This is one of the big predictions of general relativity, one of the remarkable things that happened in 20th century physics, that the universe evolves, is dynamical, its geometry changes, and now we have a whole a detailed understanding of that. But we don't really know, sort of the the questions of the origin. Sometimes people call it the Big Bang, where the universe come from. Because at that point, you see, the universe is so small that these peas and potatoes start to kind of interact, be of the same size. So there has to be somehow quantum and quantum gravitational or quantum space-time. So understanding that, of course, is a big thing. Then, of course, there are, in the standard model of cosmology, there are things like, for example, we notice that the universe is not only expanding, but the expansion itself accelerated. Someone, it's like, imagine accelerating your car. And so what's the origin of that acceleration? Sometimes it goes under the name of dark energy, a little bit of a misnomer. And there is also the issue of sometimes when you look at these the initial state where the universe comes from, and if you really want to get everything that you get in the universe, and you take into account everything that exists, then it seems like the initial state is extremely fine-tuned. And so that there's no real maybe good understanding of this. All of this goes into quantum gravity. People would, of course, mention black holes and whatnot. But for me, it's even the nature of quantum theory that is important. For example, like how come that there is this divide, as you said, like general relativity, it's about big things, but the big things are classical, like this napkin that I was throwing, right? Okay, and the little things, these p's, right, quantum things, are going around, fuzzed up. They go over all sorts of trajectory. They're probabilistic, but these probabilities are not casino probabilities. They can interfere like the waves in a pond and so forth. How come that there are these two sides of the same nature, right? It doesn't make any sense, right? I mean, this classical big things somehow have to come from small things. And so nature is one. So there has to be one way of understanding. And so for me, that's maybe the deepest mystery, right? How would you understand both in one go? And I think that's what this thing that Tristan and I are talking about in the book, Weight of Quantum, is really also useful for, apart from cosmology and all the other things that I mentioned. Is this a good answer?
Sounds good to me. Tristan,
right. Yeah.
Talk about the prediction of dark energy.
The prediction of dark energy. Let me, first of all, just connect to something that George was saying. So this fact that we have the theory of the very small and the theory of the very large. Well, every theory, every self-respecting theory ought to also kind of predict its own limitations. And these theories do. So for example, if you're trying to see something smaller and smaller, like for example, with an optical microscope, you can only see so little because the wavelengths of the visible light, the smallest wavelengths are, well, not very small. They're only about whatever it is, 300 some nanometers or whatever that is. But then use an electron microscope and use a better and better device. And you might think that, well, you can increase the power of this device in order to see smaller and smaller effects. But actually, the theoretical answer is that no, you cannot go arbitrarily small. There is going to be a smallest possible limit. We call it the Planck length. But aside from the names, the point is that that distance is the distance where your probe, when you're probing something, you need to send the probe kicks the target and then bounces back. And from how it bounces back, you can tell the shape and size and form of that object that you're studying. And when that probe is so energetic, so it has such a small wavelength, we would say, in order to see that object, it ends up disturbing the object so much that, in fact, gravity becomes very relevant. And at that point, you are irrevocably changing the target that you're watching. So that's the smallest limit to which quantum theory can possibly address. It is extremely small, nowhere near our tabletop experiments and so on, but it exists. On the other side, on the size of the large, there is obviously the size of the universe, the most distant things that we can possibly see, the optical horizon, if you want to call it that, or whatever, but basically the size of the universe. And again, that is determined by the fact that the speed of light is constant, that it takes some time for that light to reach us. And well, the big space-time, definitely this is the realm of Einstein's general relativity and gravity. So lo and behold, gravity is there again. Notice that gravity somehow sets both the huge size limit and the smallest size limit. And so this is one of the key points in our book where we are exploring this fact that gravity is actually throughout. It affects both of those limiting possibilities. And so therefore, it ends up, because it functions at both ends, it connects them. And that's why we're able to make some predictions, if you like, of some characteristic scales that would be relevant. For example, one of the characteristic scales, 10 to the minus 3 eV, whatever that is, electron volts, a particular scale that otherwise appears out of nowhere, turns out to be just the geometric means of these two scales, appropriately weighed. And so our approach to this ends up giving a kind of new way of addressing some of the things. Why is the electron as heavy as it is or as light as it is? Why are the neutrinos so gossamer light? Why are the quarks so heavy? Why? So some of these answers now can be, some of these questions can be now answered. And so this is the framework that we have been developing. And so the prospects for us as theorists that we now can actually have a handle on such questions, that is for me the most fascinating part of this story.
And also, doesn't it solve, in some sense, your proposal, what is considered to be the most embarrassing prediction in all of science?
Absolutely. So among other things, it does answer a very careful analysis when you take into account this connection between the extremely large and extremely small, again, by gravity. When you take that into account, we have done this calculation in a not terribly novel way, but in a novel reapplication of something which actually we learned from our erstwhile colleague at University of Austin, Texas. And we were able to produce a calculation that actually gives a better, much better answer, maybe not exactly on the nose to the 16th decimal, as in some cases might be expected, but a very good answer for that, as George was describing, that pressure that seems to be pushing the universe to not only expand, but expand in an accelerated fashion.
Yeah.
So that dark energy.
So you guys are being slightly too modest. So let me be immodest on your behalf. When you calculate what's called the vacuum energy, which is basically the thing that's pushing the entire universe apart, the number that you get from quantum field theory, which, by the way, otherwise predicts everything to 14 decimal places correctly, is 10 to the 120 powers wrong from the actual number that you get. So in other words, you'll get, they said the number is something along 10 to the minus 3 electron volts. The number you actually get is about 10 to the 117. So this is the worst prediction ever in the history of science, and yet it comes from a theory that is so well tested that on Earth, when we make measurements, we get them right to 14 decimal places. And so their proposal, Tristan and Djordje's proposal, might actually solve this gigantic tension. That's one thing that's very, very cool about it. And then the other interesting thing about it is that your proposal has some, Djordje, you mentioned this before, has some real effects on quantum computing, right? We're thinking about quantum computing today. So what
Yeah,
is
so you mentioned one thing that is that there is that embarrassing computation, right, of what's called the vacuum energy. Um, so and yes, here you basically get the connection between what that's observed thing that pushes the universe to expand to an accelerated expansion, and these scales are very small and very large. Um, but there is even more embarrassing a number, and that is if you really look at the initial state that the universe had to sort of start from. I mean, of all the possible states in order to produce what you basically see in the universe. And that's even like you said 10 to the 120, so 1 followed by 120 zeros, bad. But this one is 10 to that number. So it's like a Google or whatever it is. It's a huge number. So you would have to fine tune sort of the universe. It would be 1 out of 10 to the 10 to the 120 possibilities. It's totally crazy. And this, you see, once you start doing sort of what we are basically saying, that the sort of the rule for probabilities becomes dynamical, like in general relativity, but in the context of quantum theory, we call it gravitized quantum theory. Then you have a possibility now to accelerate computation. The same way that quantum computers, because of this ability to go between two states through all sorts of possibilities in between, as we were illustrating with the napkin, compared to classical computers, now you sort of get another sort of boost. Okay, so if you were to imagine a universe as this gravitational quantum computer, so you would now have enough ability to actually start yourself. So in other words, the universe would be computing itself, and then this even worse fine tuning problem, as people say, of the initial state would appear natural. So maybe quantum gravitational computers even more powerful than the ordinary quantum computers, and that's essentially needed to understand really the whole universe cosmology, quantum theoretically.
and this, sorry, go ahead.
When you talk about quantum computing, people kind of in a more I don't want to say practical sense, but like people are worried about like, oh, our bank passwords are all going to be useless and Bitcoin is going to be null and void and all of this digital systems that we all know and like use for our convenience today. Like, what is the impact on that?
Well, I mean, okay, so definitely, you see, Tristan and I worry about these foundational things, but we have many friends who work really on actual quantum computation and quantum information, and so as that's the reason why people are investing so much, precisely because of what you just said, Eric. But you see, there's also something called quantum cryptography. So people are trying to devise sort of protocols of really understanding how information could be protected, etc., in that sort of new quantum world. If there are quantum gravitational computers, if the universe is like that, then we have another issue to worry about. Personally, I don't think we are there yet in addressing those questions. There are people who have asked questions before. Let's say when people try to change quantum theory and then always something wrong would happen, people would say like, oh, okay, if you change the quantum theory, what will happen to quantum computers? And so this debate or this discussion has existed for some time, but it's far removed from any practical implication. On the other hand, quantum computation and quantum information, that's a field where people are making strides. Whether we're going to have something, that technology happening in any foreseeable future, we don't know. But, whenever you're developing something like this, you also find something new. Okay, so it's bound to be useful And so, but quantum gravitational at the moment, I would kind of shelve it because it's too far in the future. I would not worry about it, but I would worry about insights that you could get from understanding quantum gravity for quantum mechanics and quantum computation. That could be useful in practice.
Is there a tie-in to? Go ahead, Tristan.
Yeah, let me just add to that. So right now, as we speak, as we talk to each other, we have video going back and forth, we have audio going back and forth. All of this is with our devices, with our computers, converted into ones and zeros, send down maybe a FiOS or whatever other connectivity you have, and then it gets received by the other computer. Now, everybody knows that none of our these devices that we use, computers, but also the wires, the whatever, maybe you use a TV direct dish or something like that, Wi-Fi, whatever that you're using, all of these things are a little bit error prone. So we have a very well developed error correcting sort of encryption. It's not the kind of encryption where you hide things, but where you embellish a little bit those ones and zeros with additional code so that the receiving computer would be able to detect were there any errors, maybe they can even repair the error, or if the errors are irreparable, they will ask for another copy of that little packet of ones and zeros. So this is why sometimes you may end up glitching a little bit when you're watching your video as we're podcasting now or so. But generally, those error correction codes are well understood. They are what now we would refer to as the classical error correction codes. Quantum error correction codes, hand in hand with quantum computation, are being developed now. And you're asking for tomorrow the gravitized quantum
gravitational. I mean,
so
some people.
I'm sure that somebody will come up with it because this issue you started the question with fear for our passwords, our whatever other sort of security issues and so on. This is a cat and mouse game. Of course, bad actors always try to use it for nefarious reasons. And then, of course, there are the white hats who are trying to improve the situation by making better error corrections, by making better encryption, and ultimately also that sort of encryption that hides information with an appropriately complicated, not just password, but the password creation and testing scheme. Right? So
is there a tie-in to AI and the acceleration with LLMs and the like predictability of like if an LLM is predicting the next word that you're going to use, and then all of a sudden it has access to, right, in quantum land, the so many more predictions or possibilities that it could be. Is there a tie-in there as well?
Yeah,
I believe so.
I
believe so, but George may have some more thought out comments on that. I will just say for myself, I'm just fascinated by how things are developing, cautiously fascinated, because I've also seen early versions of ChatGPT and so on make absolutely ludicrous mistakes. To just give your audience a very simple example, one of the first versions I asked, how long before the moon spirals down and smashes into the earth? And the ChatGPT responded with a nice, very well-written first paragraph, just to let me know that they were thinking about the question. Then the next one, it said, it has been determined that the radius of the moon, the distance of the moon from Earth, is increasing by, I believe, 2 centimeters in a century or something like that. Third paragraph, from that we can conclude that the moon's orbit is going to decrease to 0.
Yeah.
A blatant contradiction in its own. Of course, it's getting better now.
Oh, no, much better. Yeah.
So I'm cautiously optimistic.
Yeah, but no, I mean, really, this is. I think there will be something remarkable going on here, and this has to do with the other part. I mean, we did mention towards the end of the book, which is much more speculative than this quantum gravity stuff. Even though there are people who are interested in doing experiments in this and so forth. And that is it possible that in complex adaptive systems, okay, you have sort of emergent quantum-like, or maybe even gravitized quantum-like behavior. Let me tell you what I mean by this. You see, there are two aspects of quantum theory I think we haven't really absorbed, even professionals, that the quantum mechanics actually teaches us something about space-time, okay, and probability, these intrinsic probabilities that obey the Born rule and so forth. But this part about the space-time that hasn't been really absorbed, and I think that's one thing that our work sheds on when it comes to quantum theory, applications of quantum theory to various aspects, because quantum theory has been applied to materials, to elementary particles, to anything in physics which concerns basically quantum phenomena. But then there's this other aspect. You see, quantum theory is a theory of probabilities. Now, the probability theory, right? I mean, you can use for anything. You can use it for weather forecasting. You can use it for, I don't know, you go and work in finances. You can work for actuary science. You can working for genetic, whatever. Okay, anywhere where there, I mean, in some sense, people say probability is the language of science because we always have incomplete information and we always work with probabilities. But quantum probabilities are different. And because quantum probabilities, unlike the usual probabilities, like roll of dice, okay? Yeah, get something out of a certain number of possibilities, and you say like, okay, I got 6 possibilities, I got 1, 1/6 was, I don't know, to get 3 out of, let's say, to roll 3, and et cetera, et cetera. You see, it's a number, and there are rules for combining these numbers. But the weird thing about quantum probabilities, they're not these numbers. There's something called complex numbers or whatever. But anyway, you can add them, and then you sort of square them in a particular way, and then they interfere like waves in a pond. But they're still probabilities. So the question is, if I take quantum theory as a theory of probabilities, not something that just describes the microscopic world, I just take it as a theory of probabilities. Can I apply it elsewhere? Like I apply probability theory for weather forecasting, and I don't know, to explain, I don't know, temperature in this room or something like that. Or genetics or whatever. And so this is what I think that people haven't really used. We haven't used that quantum theory is a theory of probabilities, could be applied to in other aspects of science and engineering. But I think where complexity is key, okay, that you have complex systems and they're adaptive. And so then the question comes, if this is really true, and then maybe even generalizations thereof. Okay, so now we're making these systems, right, that whether you sort of think that they're naive, like the early versions of ChatGPT, but I don't know, you look at your Google Translate, you say like, that's pretty good, right? But Google doesn't speak Chinese, doesn't speak any of these languages. It's just basically, right, following a set of rules and, and based on this enormous access to data and so forth, following this set of rules gives you a pretty good answer without knowing how to speak. But okay, but how would it speak? And maybe this is where some of these things would enter. Because if you look at how today you make images and so forth, you use classical probabilities, right? You manipulate classical probabilities in very ingenious ways, okay, to have all the images and suddenly you get a new image of a cat or a dog or something that didn't exist in all of these images. But you see, what about if you use these quantum probabilities? Or maybe even this generalized one that we argue that exists in quantum gravity. We haven't thought about this. You see, this is what I also said, another thing. We know that some laws are emergent. But this is another interesting thing. When people say laws, what are these laws? We're talking about the origin of the universe. We say like, well, if the universe computes itself, maybe these regularities of computation is we as intelligent agents of a certain ability perceive as laws, as regularities. Okay, good. But why can't we do that? And what about, as you said, like some ET or somewhere else, maybe they have better cognitive abilities. Why would we even able to do that? And I think this is an interesting possibility that you see, as you develop complex systems, the new laws emerge because of complexity. Now, lots of people have said things like this. But these laws are probabilistic. Lots of people have said that. Like, I don't know, second law of thermodynamics, right? That's something probabilistic, like, okay, heat follows always from hot to cold, not the other way around, has to do with disorder, this mysterious word entropy on it always increases and so forth. But what about, new concepts like entropy and the probabilistic laws for those which are not classically probabilistic, but probabilistic like these quantum probabilities? Now, I think that might happen, and that would be, I mean, if you think that quantum gravity is huge, which I agree it is, okay, it's this leftover legacy of Einstein. I think this would be really huge if true, because it would open up something that we really do not understand, or we have just started in some naive and simple ways, let's say simple from some futuristic perspective, to understand now. It would be a completely new realm. So I would say that yes, if you integrate all of this, intelligent, whether artificial or naturally evolving agents, information gather utilizing systems, whatever you want to call them, whether extraterrestrial, whether here terrestrial, whether artificial, and you start using this quantum probabilities, maybe you will get to a point where, well, what we have in science fiction, intelligent computers and things like that.
That's kind of, it goes a little bit with what you said when we were discussing before offline, when you said everything in some sense is quantum. And to me, like the way that Samir had described it to me before, but was kind of like there was like something that didn't really fit with that. But the way that you said everything in some sense is quantum, like just intuitively made like why would it not be? And so that's what I thought. And maybe Samir, you, because we had talked about that separately after the call, but maybe Samir, you can explain kind of what that dichotomy is a
Yeah.
little more
So let's
because
do that. And then, Tristan, you should fill this in, please. So, one of the biggest embarrassments in my opinion, all of science was perpetrated by the famous Niels Bohr, where he basically said that there's a classical world and a quantum world. And that to make sense of quantum mechanics, you needed to make a measurement in the classical world. And then that told you what the probabilities were in the quantum world. But the problem is that anytime you make a measurement, you make it with a machine of some kind. That machine is made up of ordinary matter. That matter is made up of electrons, protons, neutrons, blah, blah, blah. It's the same stuff that you're measuring. The measuree and the thing being measured are the same thing. So this whole business of the measurement problem in quantum mechanics is an absolute embarrassment. How can you separate the world into quantum and classical? It's the same thing all the way down. And from what I understand of your proposal, it might solve this absolute absurdity.
It might. Let me just expound a little bit on this separation. So you mentioned all of these apparatuses or machines, let me just call them machines that do the measurement, whether it's just a simple voltmeter or something much more complicated. By the way, just go on the internet, find any pictures from CERN, which is, by the way, a kilometer size installation, but a particular detector, as they call it. It's a huge room where if you look really fine there, if you zoom in on the picture, you'll somewhere see a human being, and the human being is dwarfed by these humongous machines. Now, at the same time, remember, we have some elementary particles zip-zapping this way and that way through the main part of that detector. Then when a certain type of event happens, it triggers the innermost layer of the detector. That triggers the next layer, the next layer, the next layer. Eventually, these events are happening so fast and so many of them, no human is ever watching them. No human is ever seeing them. They all get recorded on some terabytes of data on some hard disks or whatever. And then graduate students and other postdocs and so on, scientists, they go data mining through that data to find the kinds of experiments, kind of events that they were looking for in order to study what exactly is happening there. So in between, when that particular event happened, and until 2-3 years later, somebody finds it and discovers that particular event has happened, you can't possibly say that the event didn't happen until it was observed. Of course it happened. So this is one of those things that are very popular in, unfortunately, what's called popular science popularizing science literature, that somehow the observer creates the event. And there is the famous question, is the moon there when nobody's watching it? Of course it is, right? And all these events, of course, happen. And so it shows you that this dichotomy, this dividing of the universe into the thing that we observe and the thing which observes it, so these machines, including the observer and maybe the observer's friend or whatever, all of that somehow is the same thing. It's all part of nature. Nature is one, as George was saying it before, and we are saying it also in our book. The point is that all of that should at some level be well described quantum mechanically. And then on the flip side of that, there are even very simple examples where we do this when we teach quantum mechanics at graduate level. For example, you'd like to describe very precisely how exactly does a diatomic molecule of hydrogen, the simplest possible atom, a single proton, a single electron, put two of them together to make a molecule, how do you determine the dynamics of that system? And it turns out, for practical reasons, for calculational reasons, for our ability to do math, to solve differential equations and that sort of thing, we cannot solve that exactly. What we end up doing is we pretend that the two nuclei are fixed and the electrons are moving around them, and we solve for the electron. Then we say, oh, wait a minute, but the nuclei weren't really fixed. Now let me take the probability cloud of where that electron is and fix that, and then see where would now those nuclei want to repossess themselves, reposition themselves, sorry. And then you keep iterating this calculation. So for purely calculational purposes, I wouldn't be so harsh on Bohr as you were. For purely calculational purposes, you have to make somehow that distinction. It's built into the framework of quantum mechanics, into how we practice quantum mechanics. But one should not confuse it with the conceptual idea behind it that indeed nature is all one, nature is all quantum. And what George and I have been writing in this book, which is, by the way, supposed to turn up somewhere in July, thanks to the publishers. We have done our job now. It's up to the publisher to do theirs. So in this book that we're writing, we are trying to describe a modified version of that quantum mechanics, which hopefully reconciles it with gravity. I've said before why gravity happens to be everywhere. So it is important to make that reconciliation, to make that, some people refer to it as a marriage, but let's not go that far. That combination of, well, gravitational physics or general relativity and quantum mechanics, it somehow had to fit together, and our computational abilities are getting better. But still, maybe because of a century of tradition, we routinely divide the universe into, what did you call it, Samir? The observed and the observed.
Yes, that which is being observed in the observer, or the,
right,
you
the
know,
observer. Right.
I find it absurd. And in fact, my entire book, there it is a statement about taking the statement that everything is quantum mechanical seriously. And it's pretty bad that a lot of physicists have what I call the shut up and calculate, approach to quantum mechanics. George.
So just wanted to say this. Yeah, I also want to say, yeah, but Niels Bohr was a great scientist, and what he said at that time, I think it was the most reasonable thing. Now, there is a sort of sharpening of that, and you know that, Samir, well, is what people call the decoherence. In other words, you say like, well, okay, so this iPhone, even though it's made out of atoms or something, is not really fuzzy or anything like this. And the reason for this is that basically any of these quantum objects are really interacting with the environment. As Tristan says, in that example from molecular physics, something is sort of sluggish, something is fast moving, and so forth. And if you take into account all of the interaction of the quantum system with the environment, then on a very, very, very short scales, if you look basically the properties, the quantum properties of the system, yes, indeed, as you make it more massive or things like that, then yeah, it will seem like it's not really fluctuating and so forth. The problem with that description is it is quantum, and the question is, where would that classical limit really come in? And why did you pick, for example, description of the system in, I don't know, space-time as opposed to energy momentum? Because quantum physics is very flexible, can go both ways, pick any way of describing the quantum system. And so what we are saying here is also in some sense philosophical, at least simple. You see, you got this quantum, it's space-time classical and whatever matter quantum divide. So make space-time quantum. I will tell you in a second what that means. And then the quantum rules make such so that fit the property of space-time. What did we say? Flexible space-time or geometry of space-time. Basically, that's gravity. That's this. And so make quantum adjust to the property of space-time, make space-time adjust to the property of quantum. So what do we mean by quantum space-time? But this is one of the interesting insights here. Okay. So the statement would be that essentially you can derive quantum theory if I tell you that there is this fundamental length that Tristan was talking about and a fundamental time, and then still assume that there are sort of classical properties of space-time, certain transformations that you do in special relativity, like Samir mentioned in the beginning, like, okay, the length and time somehow depend on the velocity, they're observer dependent. Okay? And so you can make that if different observers see different space-times, but they're in superposition. You can make them consistent with this length. Because, you might say like, okay, if my fundamental length is this and I'm moving with respect to you, wouldn't it shorten? You see, in special relativity, you're going to have a fundamental length or fundamental time. Okay? And so to make these consistent, you actually can derive superposition. And actually, because of these properties of space-time, that it sort of looks in all directions the same and is somehow homogeneous in special relativity, at least, then without bending, without gravity, then you could actually derive sort of this Born rule. And then you say like, oh my goodness, if I were to bend space-time, something would really bend to this rule. Okay, yeah. Very good. So go ahead.
That's the perfect segue into what I want to ask you, in fact.
Okay.
The perfect segue is, how are we going to test this? What is the test? What are the things that you guys have put together for the test? Let's talk about the third slit. Let's talk about ABC.
Yeah. So let me just, let me just finish this thing about the classical. So the thing would be that in some sense, all these different space-time are sort of slices in a new thing called quantum space-time. And like in quantum physics, some people have heard about the uncertainty principle. You can determine, let's say, the position, but then, momentum is not known. You determine momentum of a particle, but the position is not known, and so forth. That they are kind of dual in that sense. And so the statement would be, you would get this classical rule, and quantum gravity would actually describe for you where you observe it. You always observe it in space-time. That is sort of the quantum variables you use by sort of integrating out, forgetting, summing over, if you want, of all these sort of dual space-time variables. So that's essentially our addition sort of to the usual discussion of this measurement problem, and how would you sort of get to classical things from the quantum and so forth. Now, how would you test this possibility, right? Then the Born rule is dynamical, curved, warped, or something.
Just to remind everybody, the Born rule is Euclidean space, flat space. Yeah. It's how you calculate distances in a flat.
Yeah. So everyone knows Pythagoras' theorem. I take a right angle triangle, right? Right angle triangle. This is a size A, this is a size B, and I have the long size C, and it's A squared plus B squared equals C squared. And essentially, that's the rule we're going to use, except we're going to do probabilities. And what people do is they do something which is called the double slit experiment. It originates from optics. That's how people found the wave nature of light, right? That people thought like, okay, light propagates in the straight lines. I don't know, bounces off a mirror using a short time. But actually, this is a wave that touches everywhere in the mirror. Those are the different trajectories that, if you want, we would have to sum in quantum theory. And what do? You throw something at a wave, hits these two slits, excites little waves. These little waves go, and like the waves on the pond, they interfere and they make some interference pattern. Okay. And that happens with electrons now. Except you say, like, what's the wave? Well, wave is this wave function, this Schrodinger thing that the satisfied Schrodinger equation, whatever it is, right? It's this wave of the electron, and you have the one for the first slit and the other one for the two slits. You add them, maybe with some coefficients, and you square them. So you can get the first squared and the second squared and the multiple of 2. All right.
Let me just interject one thing here for everyone who's listening. The reason this is a paradox is that you can fire one electron at a time at the slits. And if there are 2 slits, eventually in the back, an interference pattern will be formed. And then the question always is, this is what confuses everybody about quantum mechanics, is how did you get interference when you're firing single things at slits? And the whole point of quantum mechanics is that's how these things work.
And our observation, it's like I said, why this happens for the electron is because the actual space-time is also quantized, pixelated if you want, okay? And that being consistent also with how time and space are described in special relativity, okay, that thing actually induces this superposition of space, superposition of the electrons. Even you would say, like, hey, they're points, they're particles. Okay, superposition of electrons, so that these 2 things, fundamental length, fundamental time, and the continuous nature of space-time would be consistent. That's why this happens. This would be that insight, new insight about quantum mechanics. Having said that, drill the third hole. And you say, well, all right, so I have the wave function for this first hole plus the second plus the third. That's like you take 3 things, you add them, and now you square them. You can have the first squared, second squared, third squared. You will have the first times second, first time with some coefficients. Okay, don't worry about that. First time second, first time third, second times third, but never, because you squared, first times second times third. You would need a cube for that. You see? And because of that, there is no intrinsic triple interference in quantum theory. The same thing is true for classical probabilities. You see, classical probabilities never double interfere. There's no double interference for classical probabilities. You see, they're numbers. You add them as numbers. But these quantum probabilities, they have interferences. So you see the rule here. Classical probabilities are such so that double interference and triple and quadruple and so forth, they all equal to 0. All right. Quantum is now the double interference, 2-slit interference is allowed, but triple and so forth is not allowed. Why? Because the rule is quadratic. So now the obvious question is, what about the triple? What theory would? And why would nature forbid this? Okay? And that's what we are claiming. Okay? So we are claiming that once you sort of quantize space-time, take into account, let's say, how a massive object, as it falls and interferes, let's say, with some grating, maybe you made it from lasers or whatever, but now it's massive, it's not an electron. You can feel its gravity. Okay? That thing, that interference pattern would be different because you would have this intrinsic triple interference and maybe quadruple and so forth later. But let's first find this one. That would be an amazing thing. Now, most scientists would say, like, nope, cannot happen by what we know. So you test it, and people test. They do this triple interference with photons, with light. Okay, we propose to do it with neutrinos because there's 3 kinds of neutrinos. There's an experiment now going in China and so forth. Maybe people will do that. Test it with anything you can test, okay, with. And then what you find is, well, I have to have a theory that will compute this triple interference because otherwise I'm measuring 0. So any bounds on that 0 are experimental precision, various effects I cannot control, blah, blah, blah. And so we devise a theory that will compute that, even in the ordinary experiments that test the Born rule, this quadratic rule for computing quantum probabilities. And then we say, okay, suppose now we take falling things that are heavy, okay, I don't know, 1,000 million of atoms or something like this, on a grating that are, nanoparticles that are on a grating that made out of lasers. There's some technical issues, so forth. Look at the interference pattern. People have done this with atoms. They know what that interference pattern is. It's kind of carpet-like, repeats itself and then repeats at some other distances. So very carpet-like, okay? And then what we're claiming, like, actually, if you take this accounts of quantum gravity, right, then actually certain parts of the carpet would disappear. Okay. And that's different, let's say, at turning on temperature, whatever other things, because that would sort of change the carpet in some random ways. But this is not random. This is very, very precise. And I think Tristan shared something with us in
Yeah.
chat.
Right.
So,
Yeah. Which
Tristan,
is, okay.
you
Yeah,
should
go
talk
ahead.
about that, because I
Yeah.
think you had mentioned that normally when you do an experiment, what will happen is that if there's other interference terms, they'll just sort of wash out the interference pattern. But in
Yeah.
this case, which we call dissipative, which is the technical term, but in this case, you're going to actually get a change in the pattern. Why don't you walk us through that?
Right. So the image that I just shared with Eric is showing it right. So on the left-hand side, both of these are simulations, by the way. They are not actual experiment photographs or so. But on the left-hand side, you see this delicate sort of loom-like structure where on the left-hand side, at the bottom of the picture is the grating. The pictures are in such a way that things are falling upward, or rather the pictures are upside down, if you like. And in this loom, right after the grating, the wave and the particles that are passing through these nanoparticles, they interfere with each other. And this interfering pattern, it kind of looks like a weaving rug, or I don't know.
I'm going to print it.
Okay. It's referred to as Talbot carpet. It finally, by the time you reach the top of that image, it then constructs that very recognizable interference pattern that we find even in introductory textbooks of quantum mechanics. The important thing is, how does this, you might want to call it loom, this sort of carpet-like structure, how does that look like when you include some of these that George was mentioning, those cubical or trilinear or triple interference effects. Unfortunately, so this is a relatively early publication 3 years ago. The simulation wasn't very good visually, but on that right-hand side picture, you can see one extremely important fact about it.
That Samir printed it.
Yeah,
that's great,
right.
Samir. Thank you, Samir.
On the right-hand side, what you immediately see is that there is no random washing out, no random noise. What ends up happening is the pattern shifts. Some of these lines where you have like coalescing darker regions, and I apologize, the picture turns out to be very hazy and very pale, but if you could
That's
zoom in
okay. I
perhaps.
shared it on the whole Zoom screen,
Right.
so people should be able to see it instead of
Right.
us, which might be good.
Right. So, so you can tell actually that those same fringes, those patterns, those darker, lighter spots, they appear extremely regularly, but with a different pattern than on the left-hand side, which was calculated using exactly just the quadratic rule, the squaring law, as opposed to our proposed modified law. Now, the particular simulation that was done here was also in some very early stages. We were limited by, the whatever gigahertz speed of the machine that was calculating it, by all kinds of restrictions like that. So that's part of the reason why it is not, sort of in your face, very obviously different from the other one. But if you zoom in, you will tell exactly that qualitative property here. It is not random. There is no random noise here. It is not what people often refer to as decoherence or dissipative or other sort of random kind of effects. It is very regular, and it is very distinct from the standard squaring rule. Those darker, lighter patterns, they shift up and down a little bit. They become broader, narrower. They look definitely different. And by the way, this Talbot carpet is fascinating. Evidently, the picture that I sent you is PNG, so it has a finite resolution. But even our colleagues' simulation has a finite resolution. But if you were to zoom in more and more precisely, it's a sort of fractal-like image. And so there is infinitely much detail there, and a lot of that detail gets changed in a very patterned way, not at all randomly, in a very predictable way. So earlier you were asking about cryptography, and well, if we can verify this in real life, if this can be reproduced in real life, there might be some ways of, encrypting stuff in those fractal patterns there.
So for people listening, you can go take a screenshot and zoom in and like rewind and then kind of listen to the description again. But anyways, Samir, go ahead.
Yeah, so let me say a couple of things because both George and Tristan are again being good scientists and are not claiming more than they actually can prove. But the fact is that if this turns out to be right, this is absolutely one of the biggest stories in science in the last 100 years, and I'm not exaggerating. So
let me just, Samir, sorry. I just wanted to mention that these simulations were done by our colleague Dave Mattingly for University of New Hampshire. We also have friend Per Berglund, who was also on this formulae for masses and so forth from University of New Hampshire. And the experiment will be done in the lab of Andrew Gerasi at Northwestern University. Also, the computation of the vacuum energy I've done with friend, Samir Robley at the University of Illinois, at the Rano-Champaign, Laurent Ferdel at Perimeter Institute, and Jerzy Kowalski-Glickman, who is in Poland at the University of Wrocław. Just to mention that it's not just us.
It's not just you, I understand. So given that this is such a big deal, if it turns out to be true, what's going to falsify? What says that, Tristan, I think you had a good take on this. What tells you that you're wrong, that your proposal didn't work?
Well, very simply, if the experiments are performed, if our colleague Andrew manages to, drop those nanoparticles through the grating and runs it through all the, rigors of the experiment, and he does not find this change in the pattern, well, then evidently this effect is absent. Now, let me just make a small footnote there. It could be absent for a fact that the effect is much smaller than what we anticipated it to be. So you need, bigger nanoparticles, as that famous animal says in the TV commercial, I need a bigger box for this T-Rex, right? So we may need to refine the experiments to try with, bigger nanoparticles, slightly different grating, more precision. That is always, unfortunately, one of those things that experimental science is not plagued by, but this is part and parcel of experimental science. If at first you don't succeed, you try to improve those results, those experiments.
Yeah. Again, another thing is, you see, I would be very puzzled myself because now with this type of story, kind of the world makes sense. But, who am I to say what the world is? The world is what it is. And so suppose it's not like this, as Tristan says. Well, I think it will teach us something about quantum theory. Because if I3, this triple interference of the third order, if that triple interference equals 0, and then the quartic and quintic and so forth, all the one, there has to be a reason for this. If really the Born rule is the rule, okay, there has to be a very, very deep reason. And right. So I would be mystified. But then on the other hand, if I look at the flip side, you would say like, well, okay, have we really thought this, through this deeply? And maybe there is really some other intrinsic reason for quantum theory. But again, for me at the moment, I have a sort of fuzzy feeling, of course, apprehension, like will the experiment work and so forth. Right. But warm and fuzzy feeling is like, okay, maybe it would make sense. Okay. But then on the other hand, if it's, nature says, well, no, that's not how I'm working. It's not my rule. There has to be a deeper reason for that, right?
So there's a couple of profound things that we haven't talked about. I'm going to summarize 3 of them and then give you 2 of them to talk about.
Okay.
So the 3 profound things that we've already spoken about is first is the prediction of this vacuum energy wrong by 120 orders of magnitude, the second worst prediction in physics, if you like. Okay, fine. All right, fair enough. Then you've also said something about your seesaw formula, right? Which is that you have this huge scale, the Planck scale, you have the very large size of the universe. You put this geometric mean of the 2 things together, you get roughly the size of the dark energy. Okay, that's quite a coincidence. That's very interesting, and that's something that comes out of this. So those are three things, right? But there are two other things that you guys are saying that are pretty profound. The first thing you're saying is that quantum gravity isn't about Planck energy. I'd like you to, it's about quantum spacetime. So I want you to unpack that statement. So that's one interesting thing. It's a tabletop statement. So a lot of the things that people have been saying for the last 100 years is just, according to what you're saying, just wrong. So that's interesting. It's worth talking about. And the second thing that's worth talking about is that we don't know. This is interesting, Eric. We know that the Higgs mechanism gives mass to all the particles in the standard model, but we don't embarrassingly know how the Higgs boson itself gets its mass.
Yeah. So
I think that this may help with. So please.
Yeah, I mean, if I may, Tristan, but actually, the last bit, what you said, you see, the computation of the vacuum energy can be extended. Okay, I'm not saying that this is completely detailed computation will satisfy anyone, but somehow it's computing bounds for these masses. And the first one, after you compute the vacuum energy, is for the Higgs. It could be done probably much, much better. Okay, and then you get essentially that when you say geometric mean, just to tell people, there's arithmetic mean of two things. When you take one thing and the second thing, you add it and you divide by 2. That's the arithmetic mean. The geometric mean of two things is you take the first, you multiply by second, and you take a square root of it. That's the geometric mean. So these formula are like that. So what Samir was saying is you take this Planckling, which is ridiculous, a 1 over, 1 followed by 35 zeros of meters. And then, whatever the observed universe, which is 10 to the 20 meters, so 1 followed by 27 meters, like that big and that tiny small. Okay, you get this observed dark energy scale. You can do it, repeat it for the Higgs, but now the Higgs mass is the geometric mean square root of the product of this vacuum energy scale that they computed and the Planck scale. And then you can go down and actually do it for quarks. Those are sort of the elementary constituents of matter, even for the neutrinos and so forth. So actually the Higgs get into it, and the Higgs is very crucial in how then the quarks and others, except for the neutrinos, get masses. This morning I was explaining to a professor from MIT how we would get it from neutrinos. He is an expert in neutrino physics. Anyway, so okay, so that's interesting. Then the second thing, as you said, is not the vacuum energy, right? And not the masses.
So the fact is that this is now a tabletop experiment.
That the scales are different. Yeah. So the usual statement, when we started, when Tristan started, when I started, anyone who goes into quantum gravity usually say like, well, okay, it's going to be in the center of the black hole. It's going to be in the beginning of the universe. Why? Because that's where, curvatures of space-times are huge, and there are things called singularities, where space-time sort of ends and whatever, basically gravity crushes itself and the space-time crushes itself. And but you see, as you said, this is tabletop. And I think this is kind of mistaken. You say, of course, there will be new view as we were talking about Big Bang, and I think also for the black holes. But the crucial aspect here is the following. You see, space-time is somehow weird, right? You need matter degrees of freedom, like, I don't know, my hands, to establish the distance of whatever between my hands. Now, of course, there are other matter degrees of freedom in this air and stuff like that. People would say, like, we never directly observe space-time. Let's say, I can say, like, look, this iPhone has a shape. And we know why it has a shape. It's hard because it's made out of things like electrons that obey Pauli exclusion. They're called fermions. They don't like to be two of them at the same place. They like to repel each other, right? So you cannot, if you press, you get repulsion. If you were to pull it apart, they would attract because they interact by photons among each other. That's an attractive interaction. That's why things have shapes. That's a basic explanation of quantum theory. And it goes back to the original atomistic ideas in the ancient world. How could this has a shape, but what's the shape of space? What's the shapes of time? Okay, I can't scoop it up. All right, it's always defined in terms of relation, right, between sort of matter degrees of freedom. And what basically this is telling us, that if you say that there is a quantum structure of space-time, first of all, it's not going to be like for these fermions for quarks and whatever, how quarks interact among each other, or the electrons, how they interact, how matter interacts, through electromagnetic force or strong force or whatever. Okay, it's not going to be like that. And that's another thing that we mentioned in the book, that the properties, quantum properties of space-times are different. And then the question is, how does that matter? When it starts to gravity, when it becomes big enough, but it's still quantum, how does it interact with this quantum space-time? In a lab, because obviously it can in a lab. And so the scales are totally different. And you see what this computational vacuum energy and massive elementary particles, even though if they're not detailed, and maybe you say like, okay, I believe in this and stuff like that, but they are indicative of that, something is going right. Otherwise, there's too many coincidences. There's like 20 numbers that would be coincidental. You basically say like, okay, so it's not just a Planck scale and, the shorter scale and sort of the size of the universe, observed universe, okay? But it's all these different energies and scales in between. And so that would say that, they are quantum gravitational too. The origin of the mass, not just vacuum energy, but the masses of elementary particles, those would be quantum gravitational scales. And in our case, yes, they're given in terms of the size of the universe and the Planck scale, maybe to some weird powers. It's not the geometric mean if you just work out all the formulae, but you can write them that way. And so the question would be like, why? Why these weird powers and something like this? Well, the answer would be, if this is observable at the scales, ordinary scale, with, massive quantum objects. And by the way, this goes back to Eric's stuff. You see, if we could do something like this, maybe there is a new microscopy here. It's not an electron microscopy, something different. I don't know what they would use it for. I would immediately think of biology, medicine, things like that, right? But maybe you would use it for something different. You see, and it's not a well-developed thought or anything like this, but you're saying like, well, you're doing something what you did with electrons. You make electron microscope. And you're telling me somehow that these waves now are different. So why don't you make a microscope out of these different nonlinear waves? Yeah, you could dream about that, right? But that's my point. My point is quantum gravity really is not about these ridiculous energies and ridiculous distances. That's why quantum gravity is also about measurement problem. Because after all, when you start interacting with matter, starts interacting with space-time, and something like this has happened, then if the quantum nature of space-time comes in, then you ask the question, why was Bohr right in saying that, yeah, the measurement is classical? Even though, of course, he knew that the description was quantum. Well, because he said like, well, that's what you do in the lab. But why does it work? Why is this true? And I think that's where quantum gravity comes in. And that's why quantum gravity becomes relevant. Let me give you a philosophical take on this, okay? And that always excites me, you see, because physics and science is not just about detailed things and then we get incredible technology that makes our lives easier or maybe difficult in different ways and stuff like that. Physics is also science in general. It's the picture of the world. It's about culture. It's about how it's about understanding of ourselves as well. Us in the world. The knowledge, of course, developed. We don't know what we are. We learn a little bit more.
And our free will.
and then we put ourselves in. And you see, I would say quantum gravity is sort of cosmological physics. It's that physics, at least from everything we knew before, like it would be sort of that finishing touch of that physics. Maybe there's some other one, also complex system or whatever. But basically kind of in the beginning, sort of explaining the origin of the world, and then why quantum theory makes sense, and why the classical world also makes sense coming out of it. And then maybe there would be also these complex systems, and perhaps in those complex systems, under certain situations of complexity and adaptability and so forth, you will get this, maybe more quantum or more gravitational quantum or something like this. To me, that picture of the world, I don't know, it's complete, it makes sense. Of course, I could be wrong, but I think even if this is not right, quantum gravity should be understood really as sort of the origin, if you want, of physics. Okay, and that's why I think its tools and its lessons would be relevant for other parts of physics as well. See, we sometimes forget the following thing. When we learn a deeper thing, like general relativity, it illuminates what we knew before. Everyone saw, I mean, since Galileo, that there is a parabola when you throw something in a gravitational field of the Earth. Of course, this was a great discovery. But now you're saying, oh, but that parabola is actually due to the curvature of space-time. That curve is due to the curvature of space-time in a limit of small velocities and small curvature. That's the kind of limit of general relativity in that Newtonian limit. The same way you might say the following. Why don't I use the language of quantum physics to talk about classical things? And you can. You can use wave functions and you can use all sorts of things that appear. It will be weird, okay? But you can use it. So I would say like quantum physics and space-time physics will be also reformulated how we think about it from the point of view of quantum gravity. So I call the quantum gravity sort of the heart of physics because you see, it's at the beginning. When we discover new things, we always go back in time, the earlier universe, okay? And now this would be sort of, okay, well, the origin of the universe. At least that's my take on it. And I find particularly exciting. Yeah, go ahead.
Let me just add to that you were asking, how come this quantum gravity effect could be possibly detected in a tabletop experiment or effectively tabletop experiment. Not everybody's dining table, but still. Think about another experiment that looks very weird, but by now you can go to YouTube, you can find videos of it, superfluidity. Superfluidity is an utterly bizarre kind of behavior where fluids go out of their container and flow outside and do all kinds of other sort of mind-bending behavior, right? And that happens also at the room temperature. Itself, the superfluid is not room temperature, but the whole experiment can be done tabletop. And fundamentally, this is a quantum mechanical behavior where the constant, where we had initially always assumed quantum mechanical effects have to be small, they have to be atomic, they have to be teeny, they have to be comparable to that Planck's constant, which again is an incredibly small amount of action. That's what we call it. Actually, angular momentum has the same units. And as a simple example, in my first class of quantum mechanics, I have the students estimate how much bigger is the angular momentum of a spinning ballerina as compared to h bar. And of course, it's some 1 followed by 34, 5 zeros. It's ridiculously small. But here you see you have a tabletop experiment that defies usual expectations, and it is a profoundly quantum mechanical type of experiment. So by the same token, this sort of experiment that we are proposing with these nanoparticles falling through a grating, that would be a tabletop experiment. Now, we are not quite sure, should it be maybe 5 times bigger? Should the nanoparticles be 5 times bigger or 5 times smaller? So we are not sure. There's a lot, devil is in the detail, as they say. But George and I are pretty sure that there is going to be that triple interference visible.
Yeah, and one thing I wanted to mention, that's presumably why Tristan was talking. Yes, so superfluidity is cryogenic. So you have to go very low temperatures, close to absolute zero. And original superconductivity was like that. What Andy Girassi is going to do, it's also going to cryogenic to minimize noises and so forth. But Tristan is right that these macroscopic quantum phenomena can exist even, well, not maybe at room temperature, but very high temperatures. That's so-called high temperature superconductivity.
Right.
And with superconductor, you know that this is a thing that, well, let's say, for example, expels the magnetic field, so you can levitate and whatnot. Like the superfluid expands the angular momentum, you cannot grab things and so forth. But and you can keep the current going around. There's no resistivity, for example, of superconductor. There is a mystery of high temperature superconductivity, and of course, people have proposed various theories. I don't think experiment, of course, always advances, and that they made many advances in the last couple of years. But there is also an interesting question. Like once you go to this, if you have a new view of quantum theory, even for condensed matter physics, like for example, For superconductors, high temperature superconductors, something called the Fermi surface is very, very complicated compared to, let's say, ordinary superconductors and so forth. Is it possible that our new understanding of quantum theory is useful in this case? I think these things are possible. This is where an interesting thing has always happened. If you understand something as basic as quantum theory from a different point of view, really, people would say, like, even if you don't get your quantum gravity experiment and so forth, would it shed light on my understanding of new phenomena, many body phenomena, and so forth? That would be useful as well.
Yeah, exactly. Okay. So let me say one thing in summary and then ask you a quick question, right?
Yeah.
So the one thing in summary that I think is just stunning from what you guys are saying is that the experiment that tests whether quantum mechanics is wrong is occurring, basically speaking, at the same scale as the experiment that tells you something about dark energy.
Yes.
That's absolutely insane.
Well, I mean, okay, you see there, you're saying like there could be a coincidence and so forth, because at the moment you see that that Born rule was tested one part in 10 to the third, which is 1,000, one part in 1,000. Okay,
yeah.
So then you basically can say, okay, well, if you're working with atomic scales and something like that, then of course 10 to the -3 or 10 to the -4 electron volts pops in. You see, as Tristan said, the devil is in the detail. I personally think that this is the most natural scale, because you see, the vacuum energy, on one side, it's a quantum phenomenon, okay? Right? It basically saying like, I can't get to zero because things are fluctuating, so I have this minimal energy, okay? And okay, so I have that energy. But then, energy is positive, so I add everything that I have, and at some point it's going to start gravitating, curving space so much.
Yep.
So what you're saying is with this 10 to the 120 is, if I'm really doing and just everything I know about quantum theory, adding this energy, at some point the space is going to be like this crazy Planck length.
Yep.
And look how big it is.
Yep.
That's the difference, right? So how come it got so big, right? And essentially what we are saying is it's gotten so big because there's so much of the stuff in it, sort of, if you want, the quantum space time, right? And that naturally sort of explains how big it is, even though maybe this quanta are very, very small, but there's a lot of them. And the thing is then, okay, the scale of vacuum energy is quantum on one side, but it's also gravitational, because you see, it appears in Einstein's equations as something called the cosmological constant. That's the thing that models the accelerated expansion of the universe. So apart from the Newton constant, Einstein equation actually have this other constant as well. Okay, but then that constant actually has, even though it looks classical, it has a quantum meaning. So that's why it's natural. It's a scale where both the quantum and gravitational come together. And you would say, like, okay, that's my naive guess, right? That should happen. Okay. And the question is, does it happen?
So, Tristan, if this is the case, right, what will your graduate students, when they become your age and are professors, will they be teaching their graduate students that's going to be different in physics?
Well, hopefully they will be teaching this gravitized quantum theory. Hopefully it will become, as they call it, canon, right? Hopefully at least some version. What George was referring to earlier, this sort of seesaw rule, or the geometric mean sort of rule that can be iterated. So we don't predict just that intermediate energy scale, but also lots of other. In fact, all the mass scales that appear in the standard model, can be calculated in this way. Admittedly, what George and I have done are back of the envelope calculations. They are estimates. They're, as George said, upper bounds or lower bounds, depending on how you look at it. So they're not very precise calculations. The particular one about the Higgs mass scale, or the Higgs energy scale, that one ends up involving a very peculiar calculation done within string theory, done by two other colleagues of ours. But that's one particular calculation where that particular result is a little better than just a back of the envelope estimate. The rest of it still expects, or we should find, maybe our students should be finding those refinements of these results. And then, as you were asking, what happens if this doesn't work out? Well, this will be what Isaac Asimov always said. Science doesn't advance when somebody yells, Eureka, I found it. No, science advances when somebody says, whoa, that's weird. Well, George and I will tell you, if there is no triple interference in these experiments, no matter how that dropping of those nanoparticles is refined, and if there is absolutely no change in that pattern, you see the qualitative change in the pattern is more easily recognizable than a quantitative shift, a little bit this way or that way.
Yeah.
So if that
the qualitative shift actually is more powerful than the quantitative shift, frankly, because there's a lot more degrees of freedom there. So the fact that you can predict what the shift will look like is a pretty big deal. Go on.
And if that doesn't happen, then I think both George and I will be saying, whoa, this is weird. Something very strange is going on. As George was telling you, there must be a profound reason why nature so steadfastly sticks to Pythagoras' rule, a little bit caricatured, but to that squaring rule when probabilities are concerned, but not when distances are concerned in our ordinary space-time. Well, that would be a profound mystery. In that case, maybe that's what our students are going, or our students are going to be doing.
Before we wrap, because it's been almost 2 hours already, and I feel like probably between the three of you and me listening and semi-following along, that we could be here for forever. But I have two more kind of pop physics questions, also because I need clips, but that's a different issue. Yeah. Wormholes, and are we living in a simulation? I know, Tristan, you're the wormhole guy, so I'll go with that one for you first. Is it possible? Because some people say oh, the math doesn't work because the wormhole will close on you or whatever. But for people listening, is it possible? Does it work? Tell people what they are.
Right. So for one thing, there are so-called traversable wormholes. By and large, the way we understand how such a geometry would possibly look like, and by the way, there are books by now written about this topic, they require something called exotic matter. Again, this is science fiction domain. You might say, Heisenberg compensators and those kinds of things that you hear, thrown off from Star Trek and such series. But actually, no. We do have examples of so-called exotic matter. There is something called the Casimir effect. So this is something that actually can be prepared, measured, studied in the laboratory, where this type of exotic matter can be done. Now, so again, this is that level of science fiction where the science is not at all bad. There is nothing contradicting known science. We do have such types of this exotic matter, but we have no idea how to make it in such humongous amounts, resources, to produce a wormhole where, never mind us traveling through, like in Contact, where Jodie Foster ends up traveling through one of those wormholes, but just toss a penny or a pea, as earlier we were talking about peas and potatoes. Never mind a potato, just try to toss a pea through it. We still have no idea how to engineer that, but it is not impossible. And so I'll say I'm cautiously optimistic about that.
All right, you're 2 for 2 on it. I'm saying there's a chance.
And then the other interesting thing is, in some sense, George, if you say that the universe is computing itself, in some funky sort of way, the people that claim that we're living in a simulation might be right for the wrong reasons.
Yeah. I mean, you could interpret it that way, definitely. Tristan always likes to say, we all like station of the string. By the way, this is another interesting take from our theory, is that that the string should be rewritten in a way we call the meta string. This is something I did with Laurent and Rob. But anyway, it's just that actually string theory is really more about quantum foundation. It is really a theory about this quantum dynamic called quantum geometry. And then, but as Tristan says, if everything is excitation of the string, then of course, even if it's with pixelated reality, You could interpret it that way. It would not be any, implausible simulation. I don't know what we get from that interpretation, though.
It makes some of the tech bros very happy.
Okay.
You can even say it poetically, something like Plato's ideas and so on, because a string, after all, is kind of like a string instrument. We are built from oscillations of that string, so you can think of us as being chords or, harmonies of that fundamental.
Sounds Pythagorean or whatever.
No, I B flat.
Okay, good.
Awesome. Guys, I very much appreciate your time. For those listening, hope you were able to follow along. Samira, your book is on Amazon. Link will be in the description as always. For you two, Tristan and George, where will the book be available and when will it be out? I know you said July, but do you have any other specifics or anywhere that people can go to check your work even outside of the book? Tristan, we can start with you.
Well, definitely. All our work is on the archive. By the way, the image that I shared with you has at the bottom the archive link there. I mean, it's not a link. It's actually spelled out completely. It's not clickable. It was just an ordinary PNG. But you can read off that. And of course, you can, search for our names. In the last, I will say, 30 odd years or so, so they say the internet was born in 91, and well, the archive has been working first as a list server, but then eventually on the web pages since about 92 or there. So lots of our definitely the most recent work is on the archive. I would suggest go there to look for it. And as far as the book goes, I can share the link in the chat.
Yeah, you have it on your website, Tristan, right?
Yes, I do, but let me share it here so Samir and Eric have it directly. The link as it is, it does look like long gobbledygook, but the most important thing is at the very end, it ends with the ISBN. So we already have the ISBN, and so the folks at CRC and Rutledge, they confirmed that is going to be the eventual link. So this link is fixed. Right now it says, of course, available, July 21st, available for pre-order June 30th.
Yeah,
I mean, it changed a little bit. Yeah. Okay. Anyway. Okay.
For you, George, you got a website or where can people go to find your stuff outside of the book as well? By the way, all these links will be in the description, and so if people are interested, they can go and check out for themselves. But anyways, George, for you.
Yeah. So basically, if you go to my webpage at Virginia Tech, and I'm gonna try to give you this, you will find. I didn't really like Tristan put this link yet, but you can find out basically my papers. Let's see, I will share it in.
You can just email it as well after. Okay, perfect.
Let's see, where's in chat? Okay, here. Okay, so I'll just paste it in here. So if you go to my webpage at Virginia Tech, you will find out what I work on. And in particular, if you go to publications, there's this Inspire citation search. I mean, Tristan, you probably have the same thing. You can find a Google citations and things like that. There's some YouTube lecture. As I said, I don't have a link to like Tristan yet, but you can definitely find all my papers if you go to Inspire. And so, yeah.
Okay, perfect. And Samir, we'll finish with you.
Okay, so what I want to say is what's really compelling about their idea is how simple it is. For a century, everybody's been trying to quantize gravity, that is to make gravity quantum. George and Tristan are asking, what if we got that backwards? What if we should be gravitizing the quantum and not sort of quantizing the gravity, if you wish? And they have a concrete prediction that can settle it. And particularly the fact that pattern changes in a way that, that the pattern actually shifts, sort of like a carpet pattern, that's pretty amazing. And that would be cool if we could find it.
Very nice. For those listening, again, thank you again. Let us know what you think in the comments. If you happen to be in the physics world and have some thoughts on it, let us know in the comments, and we will see you guys next time. Peace.
Thank you, Eric.
Thank you, Eric. Thank you, Samir.
Thanks for tuning in to the World XP podcast. If you want to watch another episode like this one, click there. If you want to subscribe, click there.